Hello everyone, and welcome to this lecture. In this video, I'll explain how to model a photovoltaic, or PV, array together with a boost converter and a maximum power point tracking system using MATLAB Simulink. We'll begin with the basic operating principles of solar panels, then study the Perturb and Observe algorithm, also known as PNO, before moving on to PI control, PWM generation. By the end of this lecture, you'll understand both the electrical system and the complete control strategy behind an intelligent PV energy conversion system. Let's begin with the topics that we'll cover today. First, we'll discuss why photovoltaic systems require maximum power point tracking. Next, we'll examine the power stage, including the PV array and the boost converter. We'll then study the Perturb and Observe algorithm and see how it searches for the maximum power point. After that, we'll look at how the PI controller and PWM generator regulate the converter. We'll also test the system under changing irradiance conditions and discuss one practical issue that appears during transient operation. Finally, we'll see how a trained neural network can replace the conventional PNO algorithm. A photovoltaic array does not produce maximum power at every operating voltage. If we plot power versus voltage, we obtain a curve with a single peak. That peak is called the maximum power point, or MPP. Operating to the left or right of this point reduces the output power. Unfortunately, the position of the MPP is not fixed. It changes continuously with solar irradiance and cell temperature. Therefore, the controller must constantly adjust the operating voltage so that the PV array always remains at the maximum power point. This slide illustrates the complete system. On the left, we have the photovoltaic array. The input capacitor smooths the PV voltage before it reaches the boost converter. The boost converter consists of an inductor, an IGBT switch, a diode, and an output capacitor connected to the load. The controller measures the PV voltage and current. These measurements are processed by the MPPT algorithm, which generates a reference voltage. The PI controller converts the voltage error into a duty cycle. Finally, the PWM block generates switching pulses that drive the IGBT. Inside the PV array block, Simulink uses the single-diode equivalent circuit. This nonlinear equation describes the electrical behavior of a solar cell. Notice that the current appears on both sides of the equation. Because of this, the equation cannot be solved directly. Instead, numerical methods such as Newton-Raphson are used to calculate the current. The complete PV array is built from individual modules connected in series and parallel. In this model, each string contains 10 modules connected in series and 47 strings are connected in parallel. This slide explains the difference between series and parallel connections. When modules are connected in series, their voltages add together while the current remains the same. When strings are connected in parallel, the voltage stays constant but the current increases. This combination allows us to design PV arrays that can deliver both the required voltage and the required current for high-power applications. The boost converter has two operating modes. When the IGBT is on, the inductor stores energy from the PV array while the diode blocks current flow to the output. When the IGBT turns off, the stored energy is released through the diode to the output capacitor and load. By adjusting the fraction of time that the switch remains on, known as the duty cycle, we can control the output voltage. This relationship is approximately given by the equation V out equals V and divided by 1 minus the duty cycle. These are the electrical parameters used throughout the simulation. The inductor value is 1.45 millihenries. The input capacitor is 1,000 microfarads. The output capacitor is 3,227 microfarads. The load resistance is 2 ohms. The diode and IGBT parameters are also specified to produce a realistic switching model. The Perturb and Observe algorithm is one of the simplest and most widely used MPPT techniques. The controller first measures the PV voltage and current. It calculates the power by multiplying these two values. The new power is then compared with the previous measurement. If the power increases, the controller continues changing the reference voltage in the same direction. If the power decreases, the direction is reversed. This process repeats continuously until the operating point reaches the maximum power point. These 4 rules summarize the entire perturb and observe algorithm. Depending on whether the voltage and power increase or decrease, the controller decides whether to increase or decrease the reference voltage. In this implementation, the reference voltage changes by 1 volt at each iteration. The initial value is 300 volts, and the reference voltage is limited between 0 and 363 volts. The MPPT algorithm only determines the desired operating voltage. The PI controller is responsible for forcing the PV voltage to follow this reference. It calculates the voltage error and generates a duty cycle. The PWM generator compares this duty cycle with a high-frequency triangular carrier signal. Whenever the duty cycle is larger than the carrier, the IGBT is switched on. Otherwise, it is switched off. This process regulates the converter and keeps the PV array operating near the maximum power point. This diagram summarizes the complete control loop. Voltage and current are measured from the PV array. The MPPT algorithm computes the optimal reference voltage. The PI controller converts the voltage error into a duty cycle. Finally, the PWM generator produces the gate signal for the converter switch. Notice that the entire chain repeats continuously throughout the simulation. To evaluate the controller, we apply a changing irradiance profile. The irradiance changes in several steps while the temperature remains constant at 25 degrees Celsius. This test allows us to observe how quickly the controller detects the new maximum power point after each environmental change. During testing, we observed oscillations immediately after each irradiance change. This ringing occurs because the inductor and the input capacitor form a lightly damped resonant circuit. A sudden change in the reference voltage excites this resonance. The solution is to limit the rate of change of the reference voltage and ensure that the controller bandwidth remains well below the resonant frequency. To summarize, the boost converter allows us to control the operating point of the PV array. The Perturb and Observe algorithm provides a simple and reliable way to locate the maximum power point. The PI controller and PWM generator regulate the converter so that the PV voltage follows the desired reference. Finally, a trained neural network can replace the conventional MPPT algorithm, providing much faster predictions while maintaining high efficiency. That concludes this lecture. I hope this presentation has provided a clear understanding of photovoltaic maximum power point tracking using MATLAB Simulink. If you found this video helpful, please consider liking the video, subscribing to the channel, and leaving your questions in the comments section. Thank you very much for watching, and I'll see you in the next lecture.